Hello, my amazing students. This is Mrs. A, and today we're talking about 2.1, which is increasing, decreasing, and piecewise functions. So, the first one that I have here for you is number 20, and we're supposed to talk about where this function is increasing, decreasing, or constant, okay? And if we remember our functions, we know that all absolute value functions are going to be V-shapes, okay? And the absolute value of x would be right here, and it would be going up at 45-degree angles, but this is a -3 shift. So basically, we're going to shift this to where it would equal 0, which would be -3. So it's going to shift left 3, and it's going to shift down 5. 1, 2, 3, 4, 5. And then it's going to go at a slope of 1 up, over, until you have a V shape right there. Okay, so it's a little rough. I don't have graph paper, but when we're looking at where is it decreasing, we would say that this function is decreasing from -infinity down to -3. So -infinity to -3, okay, and paren, and then it's going to be going down. So we're going to be increasing from -3 to +infinity. And it is not constant anywhere. So that is our function. -infinity to -3, -3 to +infinity. And that is number 20. So when I went over and looked and made sure that I had the answer right, I noticed that they also put relative minimum of -5 at x is equal to -3. So I forgot we were supposed to give the area that it is decreasing, which is from here to here, and the region where it is increasing, which is from here to here, and then we're supposed to talk about relative mins and maxes also. So that was an additional point on number 20. Okay, so now on number 22, we have -x squared minus 8x minus 9. And in looking at this, I know that this, because of the negative in front of the x squared, this is a downward facing parabola. I also know that the vertex of the parabola is always going to have the x value of the vertex is at -b over twice a. So this is my formula for the x value of the vertex. So I plugged in my -b, which was 8, and my twice a, which is always in front of my x squared term, and I got -4 as being the vertex of this downward facing parabola. So then I plugged in a couple of values here. At -4, I wind up plugging it in and I get a 7. So at -4, I go up to 7, and I knew that by plugging in a 0, I get a -9. So 0, -9 is a point. We also know that this parabola has symmetry. So if it's 0, -9, then 4 steps on the other side of the vertex will also be a -9. So I know that's going to be at -8, it's going to go downward. So my parabola is going like this, okay, with a relative maximum at -4, and that maximum is a value of 7. So we would say a relative maximum of 7 at -4, and it is going to be increasing from -infinity to -4, excuse me, and it will be decreasing from -4 all the way to +infinity, because even though this looks like a small region here, remember it continues on forever. So we just say -infinity to -4 and -4 to +infinity for my increasing and decreasing. And that is number 22. Okay, so here we go with number 23. And then number 23 is a graphing calculator problem. This was the formula, the equation that they gave us, negative x cubed. So it's going to be a cubic. Remember, cubics have a squiggle in the middle. And these were the parameters that they gave us for adjusting the window. So I have my, remember I went to my x equals key and I plugged in the formula right there. Your x equals button is on your top left. And then I went to my window, which is the second key, and I adjusted the window to be what they said. So -3 to 7 on the x, okay, and then -20 to 15 on the y. So once I did that, then I graphed my function, and it looks like a cubic with a squiggle in the middle, okay? And I can see where its minimum is, and I can see where its maximum is, but I don't know the exact points. So I'm going to go to my second button and my calculate button, which is right there above my trace button, okay? And then when I calculate, it shows me a menu, and I'm going to calculate my minimum and my maximum. So we'll do the minimum first. Okay, so then I hit enter, and then it asks me, am I left bound? Am I just to the left of the minimum? Well, if you look where my cursor is, I am not to the left of the minimum, I'm to the left of the maximum. So I'm going to have to move my cursor all the way over to the left with my little left arrow until I get to the left of the minimum, because that's what I'm testing for right now. So now that my cursor's to the left, I'm going to hit enter, telling him I'm there. And then it says right bound. So now I have to move my cursor to the right of the dip, okay, because I'm trying to find out what that is. And about there should do it. Okay, you can see where my cursor is now. And now I'm going to hit enter. And then it says, would you like me to guess? And I'm going to say, yes, please guess. So I enter one more time, and it gives me its best guess, and it does this through a series of iterations. And it says 0.9999841. Okay, well now the real answer is not 0.999, it's really 1. If you plug in a 1, you have your minimum. Okay, but what this does is it does a series of iterations, and when it thinks it's close enough, it gives you its guess. Okay, and then so 1 -8 is that minimum. All right, and I wrote 1 -8 here because we're going to evaluate this in a minute, and then we're going to go find our maximum. So we're going to have to go through the whole process again. So we're going to go second, calculate. Okay, and we're going to go down to maximum and hit enter. Okay, and the leftmost is here. Okay, and we're going to hit enter. Okay, and the rightmost is here, and we're going to hit enter. Okay, and then would we like to guess? Yes, we'd like to guess. So we click yes, and it gives us 1 point. Oops, I don't think I got to the, oh, you know what? I'm looking at maximum, and I am not to the left. So I got to go all the way back to the beginning. I did not have my cursor in the right place. Sorry about that. Let's try one more time. Okay, so I am left of my maximum now. So I'm going to hit enter. Now I've got to move all the way over to the other side. And now I ask it to guess. And it says 3 -4. 3 -4, which is the maximum. Okay? So now we have both of those points on the board. And we know the basic shape of our graph. So where would you say it has a decreasing function? Okay, so since we know that that minimum point is going to be 1 -8, okay, 1 on the x is the value. So this function is decreasing, okay, from -infinity to the minimum, which is 1. Okay, and then I'm going to go ahead and put parens. Remember, we didn't use the brackets because we figure at the turning point it's not increasing or decreasing, it's just kind of turning. Okay, so negative infinity to 1 is the decrease, okay, and then we're going to have an increase to the right of that from 1 until we get to 3, so an increase from 1 to 3, and then our function decreases again. So it's going to decrease from 3 to infinity. So it's going to decrease again from 3 to infinity. Okay, so because it's cubic, it has 2 turning points. All right, we can always have one less turning point than the degree of the polynomial. So we can have 2 turning points, and it does turn twice. So it's decreasing in 2 different areas, and it's increasing in between them, and you can see that right there. So that is number 23, and you need to know how to use your calculator because you could have one just like that on your test. Okay, so now we're looking at number 29, and number 29 looks very interesting, and when you put it on the graphing calculator, it does look like an interesting function. Okay, so I played with this a little bit, and I expanded the window so that I could make sure it did not have any other turns or quirks, and this is really all there is to it. So that's our function. It approaches the asymptote. It's got a horizontal asymptote at y is equal to 0, and it does it on both sides. So it continues, once it peaks here, it continues to go off towards positive infinity and negative infinity with nothing else happening. They're just going towards that line. So now our maximum is obviously going to be right over here. Our minimum is going to be there, but without plugging in, giving it a little bit more definition here, we don't know exactly where that is. So again, we would do second calculate, and we would go to our minimum, okay, and it says left bound, and I've got to kind of move it a little bit so I can even see where my cursor is, and my cursor was kind of close to the origin. So I'm going to move my cursor over here left of my minimum, and I'm going to hit enter. I'm going to move my cursor over to the right of the minimum and hit enter again. And then, yes, I would like it to guess, so I hit enter again. So that should plop the cursor right down there at that minimum point, and it does. And it gives me its best guess, which is -1, -4. Okay, so that bottommost point is -1, -4. All right, so I'll make a note of that, and now let's go look at the maximum. Okay, so I'm going to go over here, and I'm going to do second calculate again. Okay, and this time I'm going to go to the maximum, and we're going to go to the other part of the curve over there, and my cursor needs to be moved right to the left of the maximum, so I say yes, enter, and then it's going to say move it to the right of the maximum, so I cursor over to the right of the maximum and hit enter. And then would it like me to guess? Yes, I would like it to guess, and it should put the cursor right on top of the mountain, and it does, and then it gives me its best guess, which is 1, 4. Okay, so we had our minimum at -1, 4 and our maximum at 1, 4. Okay, so here, when we're talking about increasing, it's from, here's our graph again. Okay, so basically it's decreasing from negative infinity all the way to the -1. And then it's going to increase from the -1 to the +1. Can you see that? And then it's going to decrease again from the +1 all the way to infinity. Okay, and this is what the book had for the answer. Notice again, don't be upset or worried about what you do at the endpoints here. Increasing, open, 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 open. They'd never include the endpoints when they're talking about increasing or decreasing. Just leave them open parentheses because you're talking only about where it's increasing or decreasing and not the turning point. Okay? And so if we were to describe the relative maximum was at 1, 4. So we'd say the relative maximum is a value of 4 at 1, at x is equal to 1. We would say the relative minimum was -4 at -1. Okay, I don't think I wrote that down here. -1, -4, not +4. Okay, so that was number 29. All right, so now we're starting some of the word problems. This is number 34, and it says that a seamstress is designing a triangular flag so that the length of the base of the triangle in inches is 7 less than twice the height. So I kind of drew something that in my mind was looking like they were talking about. Okay, express the area of the flag as a function of h. Now we did this in several instances with rectangles where we're trying to get down to one variable. So then I took this information that the base of this triangular flag is 7 less than twice the height. Okay, and I know that the area of a triangle is 1/2 base times height. So now my job is to get rid of the base here and represent the base in terms of height, which I've already done right there. So now the area is going to be 1/2 the base, which was 2h minus 7, times the height, which is part of the area of the triangle formula. So now when I distribute this all out, I get the area of the triangle is h squared, because the 1/2 and the 2 will cancel. We end up with h times h, or h squared. And then the 1/2 times the -7 gives me -7/2 times the h, and there you have it. Here's your formula for the area without any base in it at all. It's just in terms of h. So that was number 34. All right, so we're going to do problem number 43. And in problem number 43, we have a box, a piece of cardboard that is 12 centimeters by 12 centimeters. And our job is to create a box by taking out little square boxes out of each side. So we're going to make a cutting and cut that out to form a box. Now each one of these sides has a shape of x times x. So each one of these little cutouts is a square. And then of course we would fold the box here and fold the box here and come up with a box. And we are supposed to express the volume of our box in x. Okay, so basically our new side length here is going to be the 12 centimeters that we started with, and this whole thing is a 12 by 12 square. So since we have two boxes that we're taking out of the length or the side of the box, it's going to be 12 minus 2x. And then again on this side, which this thing is square, it's going to be 12 minus 2x would be the other side. Okay, so the volume would be the 12 minus 2x times the 12 minus 2x times the x that is now the height of that box. So here is our volume expression right here. Okay, so x times 12 minus 2x, 12 minus 2x. So side times box height, there is the volume of the box. And then we can simplify that because this comes from taking a 2 out of this one and taking a 2 out of this one and pulling it out to the front. So we get 4x. And then each one of these becomes a 6, take away x. And so we have 6 take away x squared. So this is the simplified version of our volume formula. Now, when we start talking about in B, we start talking about the domain of this function. Well, since the original side length, we divided by 2, so the original side length was now 6. And then the x is what we're taking away. Doesn't make any sense at all for the cutout to be longer than the side. So our domain winds up being 0 right there would be if the x was 6. So that's the very max that our x could be, would be a 6. So we've got 0 is less than x is less than 6, where x is that little cutout, okay? And then we are to graph this thing and find the maximum that the box could be, okay? So I put this formula right here, 4x times 6 minus x squared, quantity squared, into my handy dandy y button on my calculator. So here is my y equals that formula, 4x times the quantity 6 minus x, quantity squared, and then I graphed it. So when I graph it, I get that cool little curve, okay? So it's looking like kind of a slanted upside down parabola, and we can find the maximum with our little maximum trace. So we're going to do second calculate, and we're going to go down to maximum here, and we're going to follow its little clues here. So the first one is left bound, so I'm moving my cursor to the left, and then I'm going to say yes, I'm to the left of the maximum, okay? And then it says right bound, so I have to move my cursor over to the right, and there it's at the top, and now it's moving to the right, and I'm to the right, so I see enter, and then it says, would you like me to guess? And I say, yes, please guess. And it guesses the highest point. You can see the cursor up there, and it says the maximum is when x is 2, okay? And y is, remember, the volume, and y is 128. That would be in cubic centimeters, because everything was in centimeters in this problem. So they're giving me the x, which is the side length of the box, and that is 2. So now I go figure out the rest of it. I know what the maximum volume is, but what I need to know is the dimensions of the box, okay? So the volume, the maximum volume was 128 when the x was 2, all right? So 2 is going to be the x, all right? And then 12 take away twice x, which is now going to be 2 times 2, which is 4, and 12 take away 4 is going to be 8. So this is a 2 by 8 by 8 box. Okay, so the bottoms are 8 by 8, and then the height of the box is 2, and that is the maximum because we graphed it and moved our little cursor to the maximum and did our little maximum calculate thingy and got it. Isn't that cool? Okay, so your graphing calculator is very valuable. So we not only know the domain of the problem, but we also know the maximum volume that can be obtained is 128 cubic centimeters, and that happens when we have 8 by 8 by 2 being the dimensions of the box. All right, so now we're moving into piecewise functions, and we're going to do number 50 on this one. And we have our function defined here for x is less than -2, -2 to 4, and then x is greater than 4. So basically these are each like little kingdoms, and each little kingdom has its own little ruler, and when you walk into that kingdom, you've got to obey the ruler of that kingdom. Okay, so when we look at f of -4, we are in the kingdom that is this first domain here. X is less than -2, -4 is in that kingdom. Therefore, we're going to plug in a -4 right into this equation, and we'd get negative 5 times the negative 4 is a positive 20. Take away an 8 would be a value of 12. Okay, so we were in the first kingdom there. And then f of negative 2 is right on the edge of this kingdom here. Okay, but the negative 2 is in this kingdom's domain, because this one says when x is greater than or equal to negative 2. So he's got to follow this rule, the second rule here. So 1/2 of negative 2 is going to be negative 1, plus 5 is a 4. So that one would be the value of a negative 2. The 4 is also in this region, so he's going to have to obey that rule. So when we plug in a 4, we got 1/2 of 4 is 2, plus 5 is 7. And then lastly, f of 6 is in this last little domain or kingdom over here. He's got to follow this rule. So we plug the 6 in for this x, and 10 take away 12 is a negative 2. Okay, so just because we are looking at these, this is a pretty good one to just go ahead and graph. So I'm going to go ahead and graph this one for you, even though this one didn't ask you to do this. So I'm going to draw on this board these three, and we're going to have, so we'll put our little grid here. Okay, and we're going to, x is negative 2 is the start of this one. So now this is not meaning an asymptote here. I just want to kind of define these little regions here. So negative 2 is one region or kingdom over here. Negative 2 to positive 4. So 1, 2, 3, 4. So we have another little region here. Again, that's not an asymptote. And then over here, we're in that last little kingdom or domain. Now, each one of these, if you look at these, each one of these are lines, okay? And the first one is negative 5x minus 8. So if that one was going to cross the y-axis, it would cross at negative 8. So that's close enough. So the negative 8 would be its y-intercept if it existed in that area. And then it would be going a slope of negative 5, which means it's going to go up this way. It's going to go up 5, back 1. Okay, so up 5, back 1, and up 5, back 1, and up 5, back 1. Okay, so I could draw this line, but remember, it doesn't exist in this part because that's somebody else's, but it's going to look like that. Okay, and this one was x is less than negative 2 was the domain, so I'm going to put a little open circle right there, and I'm going to erase the rest of it because we're in somebody else's territory here. Okay, but if I continued it on, it would have crossed at negative 8 because its graph was negative 5x minus 8 was y, and that is a line that has a slope of negative 5 and a y-intercept of negative 8, but it just never gets there because that's outside its region. All right, so then from negative 2 to 4, the ruler is 1/2 x, so y is 1/2 x plus 5, which means it's going to have a y-intercept of 5. 1, 2, 3, 4, 5. And it's going to have a slope of 1/2, which means it's going up 1 over 2. Okay, up 1 over 2. And then, let's see, up 1 over 2, so it should be all the way over there. Okay, and then down 1, back 2 would be about there. Okay, but remember this one went from negative 2 included to 4 included. So we can go ahead and graph this line, including a darkened circle there and a darkened circle there, and all of those points in between. that would be the line y. Oh, I wrote over my line there. Y is 1/2 x plus 5. Okay? So a piecewise function is just a function that happens in several pieces, right? And now we're going to do the last bit, which is greater than 4. And when x is greater than 4, we're going to follow 10 minus 2x. Okay? Well, now we don't even start this. 10 would be way over here, but this thing's going to be going down at a slope of -2. All right? So when I plug in a 4, it's going to be 10 take away 8, which is 2. So I'm just going to put an open circle right here at the 2. And then from that point, which is where it would end up if it was coming down from 10 here, then it's just going to go down 2 over 1. And it has a negative slope, down 2 over 1. And we can draw that last little bit of the piecewise function. That was number 50, which did not really ask you to graph it, but I thought I would anyway. Okay, this one is an interesting one because we have a function that exists everywhere except when x is -1, and we'll see why that is in just a minute. And then we have a value that is what the function is going to exist when x is equal to -1. Now, if you look at this function very carefully, you can see that at x is -1, the function is undefined because a 0 will result in the denominator. But if we factor this numerator, we get x plus 2, x plus 1 over x plus 1. Now, if we make the provision that x cannot be -1, which is the provision they gave you, then we are free to cancel the x plus 1 and the x plus 1, and we're left with a linear function, x plus 2. So we can graph this as a line, x plus 2, everywhere except we're going to leave a hole when x is -1. And then in place of that hole, we're going to put a darkened circle at 7. So this is what this is going to look like. Let me get another board here. Okay, so the line is x plus 2. So here's our graph. X plus 2 is a line of slope 1 that crosses at a y-intercept of 2. So here's our line. It's got a slope up 1 over 1, up 1 over 1, and here is our line, x plus 2, which exists everywhere except when x is -1. So right here at -1, we're going to have a hole. Okay? And that hole is where the only thing that's outside of that domain, and instead of that little hole at -1, we're going to say at -1, 7 is what we're going to replace it with. So 1, 2, 3, 4, 5, 6, 7. Well, I'm off my chart, but let's pretend that's the 7 right up there. And that would be the graph of that piecewise function. And that is number 60. And I think we've given you a good idea of everything you need to know for 2.1. And this is Mrs. A, and may God bless your day.